So this is going to be, I think, that tutorial. I will try to attempt to solve questions. I'm not going to really solve them, but I'm going to more of guide you on how you could solve them. Like for instance, things like integration. So from calculus 1, we expected that you are able to solve such things. So so let's just read. So for each of the following differential equations, your D is find the general solution. So you're supposed to find some sort of y is equals to something if possible, and find the largest interval over the general solution is defined. So we're going to find, should I say, the domain of whatever that is our general solution. So then the last part will be finding the transient term, right? So yeah, so let's try to solve it. So y, okay, that's all. Y prime plus 2xy is equals to x power 3. So this is one of the problems that we are going to use our integration, I think they call it integration factor, where we're just going to find some function we're going to multiply on this function such that this thing really look like it was some sort of product rule. So what you actually do, the standard form is y prime plus pxy is equals to, let me say, some g of x. So our px here is going to be exactly that. And to find the integration factor, you said mu is equals to e integral of px dx, and our px here is just that. So you can just sub it here to x, and then from that, I think, given that you can integrate, this thing will obviously look like, I think it will look like x squared. So this is going to be integration factor. So what we mean to say is that if we take this term or this factor, multiply by it throughout here, it will yield out something that really look like a product rule. So it's going to be e x squared y prime plus 2, let me write it, e x squared, but the x squared is on the power 2xy is equals to x3. So remember that the product rule kind of look like it says f dot g is equals to f prime plus g prime f. So this is exactly how this thing look like. If that is a case, that means from this one we can find out the function so that we're interested in. So it's going to be e x squared and some y. If I differentiate this function, it's going to yield out this thing. Alright, then we can now continue. Plus, oh, not plus, this thing caters for everything that is here, right? So you just have to remember that you multiply by integration factor, so the ex is supposed to also be here. Then it's going to be ex squared, x squared, x cube, I think. Here it was cube. So from here, to undo differentiating, we have to integrate both sides in terms of x, both sides. So from that, this integral and differential and differential will cancel each other. It's more of like differential means a very small thing, and if I add the small thing, I can get the big thing. For instance, if I differentiate, if I integrate something that is a partial of x, it's going to be just x. So I'm adding small things from somewhere to somehow, and then I get a very big thing. So then I come here now, then this one will yield the same thing as it is. And then if you integrate here, you're going to use I think by part your uv and all that. I think given that you integrate well, I think here, if you do integration very well, it should be something 1/2 open x squared ex minus e x plus c. Because of our integration you get a constant. Also the side we got a constant, but if we take it on the other side it's just constant plus constant, giving out another constant. So really now you can see that this thing was exactly from sort of a by part thing. So you want to make this thing y is equals to, so I'll have y staying here, then this thing I'll divide by it throughout, and if I do I'll have x squared here because I'll remove it there, minus did I miss anything? If I divide by it here it's going to be that, and if I divide by it here it's going to be nothing all over 2 plus c. Yeah, yes, this thing is more like I'm factoring it out. It will cancel that, it will cancel that, and it will cancel that. Probably left with something like that, and this is our function. If we're given an initial value theorem we could be able to solve for c, but now you're interested in the first question, the largest domain. So this thing behave more of quadratic, so it's also differentiable everywhere. Quadratic look like that, and it exists almost everywhere. So we could say x is an element of from negative infinity up to positive infinity because this thing exists everywhere. Remember we're deducting our decision from that. So what is the next question? Determine the transient term. Okay, differential equations are used to study very dynamic and complex cases like in fluids, electromagnetism and all that, and a lot of other engineering and physics field that I used to define, we study using differential equation. So when we talk about transient term, we're literally looking for after so many time, like very long time, how will this thing behave? So a transient term is a term that is going to disappear as time goes on. For instance, let me say I have a graph that that is oscillating sine and also bounded by some x. So as time goes on we're interested how this thing looks. So as time goes on this thing is getting really straight. I think this function will be some sort of, could be any trick. Let me just say sine x, but it'll be bounded by something exponential. I don't know, it's going to be e or negative x or something like that. So this function is they call it, I think if we are studying differential equation also they call it a stamping spring type thing, because as time goes on if this is a pendulum, it's swinging and then it's dying out. So that's what is happening here. So when we talk about transient time, we're interested on what will happen on the behavior of the particle or the fluid after a very long time. So what we're going to do, we're going to look at our so the term that will be dying here, far as I can tell, I think after dividing by that e power something, I was supposed to divide by x squared here, so such that this term is a term as I push it to this term limits as x goes to infinity of ex squared. This term just goes to 0, it dies out. So this one dies out. So literally we're studying this thing for a very long time. Scenario, this one won't be significant for our results. You could just focus on this one because we know that after a very long time this term will die out, but this one will be the more interesting one. So that means this thing might try to behave exponentially, but after some time it will just be determined by however this function is behaving. And then our second problem, b, they're given 1 plus x and then dy, forgive me for my handwriting, all over dx minus xy is equals to x plus x. Then remember our standard said this thing's supposed to look like px y is equals to some g of x, such that you can find the integration factor by saying integral of whatever that is px dx. So in this case you see that our prime is accompanied by something we don't like. So I think the first step we're taking whatever that is accompanying this, remove it. Then we have y prime here minus x all over 1 minus x. Y is equals to x minus x squared. So I think from here you see that now it's in a standard form and then so I think after dividing by that term I have to divide by it throughout. It was 1 minus x, so it gives us our new p, our new g of x. So if you want to do integration factor, now it's going to be e, just integrate 1 minus x dx. The common mistake that people do is when they just did now the time I was taking my p of x, I didn't take a negative with it. So it has a negative there, it's supposed to go with it here. This is the negative, because you can put it inside. I just want to take it outside so that it's easy to work with. I think it's better if I take it inside because also the x below is negative, so I'll have negative x. Also below there is negative x. I can add 1 and I can subtract 1. You know, adding and subtracting the same thing really means I did nothing. It's more of like a displacement. I haven't seen that I came back, so 0 displacement. So we can now let me integrate this because it looks easy. I'll have integral. I can divide this term like that. This take that and that take that. So it's the integral of 1 minus x, 1 minus x, and the next one is would be minus 1 minus x dx. Then it's become an easy integral now because this is just 1. This thing, that's why you get your ln, if I'm not mistaken. So my answer is going to be e ln from that one. We'll get ln 1 minus x. Then I'm going to get, remember ln is supposed to get absolute plus x from this one, integrating just 1. So I think it needs to be negative. Yeah. Then now we have our mu. But I just noticed that I could still break down my solution where I have the ln cancel the e, they will have just 1 I'll have 1 minus x, 1 minus x, and then this goes with that one, like literally dividing by it. So I think that's my more simplified mu. So we can take this mu now, as much as we were doing, multiply by it throughout on our mother function. So if I multiply by that mu throughout, I'll end up having 1. I'm multiplying by mu there. I'll have 1 x all over ex, of which is that mu, and then minus x all over ex is equals to x plus x. This is me after skipping steps, simplifying. But if you feel like I didn't clarify something, you can just, but I think yeah, I just skip a couple of steps to arrive here. Then this now look like a product rule. We can do what we've been doing. This is going to be our first function that was not differentiated. This is the function that, remember there was y here, that was differentiated. Then you can put it under our differential, then x, whatever that was here, ex. then you know that we have to integrate both sides also. Integrating this side will just yield out, there's supposed to be an x here, will yield out whatever that was here. Now we have to face this integral. I think this is our last integral we're facing in this problem. Okay, so also we can do by parts. You can do by parts. But to save time, if you do that integration by part, you'll yield out a result that, let me just write it here, integral of I use a integrating calculator because not writing a test. Obviously you expected to revise things like your integration by parts, yield out something that look like negative x 1 plus x e negative x plus e negative x plus 2 open 1 plus x e negative x. The thing is there. Cool. Then we can substitute whatever that we have back to the expression and solve for y. Then after doing that, our y is going to be x, y of x 2 minus, going to be a very long one. Hope that I didn't make mistake computing. And then some constant that we got after integration, 1 plus x, which will then can simplify it. I think I can, yes. And then whatever the constant was, e to the x1 plus x. So this is our function, our solution. So from here it's easy to notice that this function can't take in value -1, so the domain will be restricted by -1. Then anything other than -1 will be perfectly fine. So our domain for interval will be just from -1. Remember, we're not including -1. Also, you can include infinity again. So this is going to be our domain for our solution. So our solution exists here, and then the transient term, the term that will disappear after a very long time. And if you think about it, all of these terms we have here, this, that, that's the same term actually. As much as you push them to infinity, they stay, or they keep growing or behave whatsoever reason, but they don't disappear. So we don't have a transient term for this problem. But to be safe for test purposes, make sure that you take we have, how many terms we have here? 1, 2, 3 terms. So it's safe to just take each and every term, like limit as 2x goes to infinity, and take limit as -x goes to infinity, and take 1 plus cex all over 1. I think that was plus x limits as x goes to infinity, and then see what we yield here. If any of them yield out 0, then we have a transient term that will disappear in a very long time. But for this case, we don't have a term that will disappear, so it's stable as it is. Then for question 2, they're saying for each of the following initial value. So they're giving you initial value. Problem: solve the given equation and find the largest interval over which the solution is defined. So that means to get whatever interval you're interested in, you have to actually find the solution to the differential equation. So, but now we won't be having c's that are crowding out in the very end, because with initial value you can solve whatever the constant that we got from the integration. So let's try to make it look like the way we want it to. I think this look like that, and now the y is supposed to be the one that is coming this side, and then equals to 2x. That's our standard. So from then we can notice that this is our p of x, So to find mu integration factor, it's going to be e integral of 3 dx, and then that will yield out e 3x. That's going to be our mu. Then you can multiply by our mu throughout, and then if we do that, we'll have e 3x y prime plus 3e 3x y is equals to 2x e 3x. Then from here we can observe that it looks like a chain rule. Then we can write it like that, which is equals to whatever that is on this side. Then we can integrate both sides. Then from here, this will just cancel the differential part. We'll be left with whatever was inside. And here on this side, we have to integrate. I think also by parts would be a very good thing to use. Okay, so let me say after you do whatever that you do, I think it's going to be by part. You have to yield out a result that look like this. And if you feel like there's a need to practice integration by part, because most of these and they depend on actually being able to solve integration by parts. So I think you have to go back to your calculus 1 and try to work around those. And then you can divide by whatever that is here to have y is equals to something, right? I think if I divide by that e power x3, and I'll have a function that look like 2x all over 3 plus 2 all over 9 plus b e, or I call my constant c. I have e 3x negative because I divided by it. And from here it's easy to notice that the domain for this function is actually everywhere, an element of negative infinity up to positive infinity. Nothing this thing restricts. It can take any value. Okay, then if we apply our initial remember we said because you have initial value theorem, we're not initial values given, so we can't have a constant unknown. So we were given that y of x naught supposed to equals to 1 over 3. Let me confirm. Yes, that's fine. Then if I sub that here, I'll have 1 over 3 is equals to 2x naught. Our x is x naught, will give us an x that's definite value, plus c e negative 3x. So yes, now we can write c in terms of x naught. Then it's more like we are trying to solve for c. Then our c is going to equal to 5 over 9. That's a 9 minus 2x naught 3, and e 3x naught. So if I skip something obviously in between here, make sure that you can follow up and see if you're getting the same result as me. Otherwise you can discuss in class how this thing then fits in as it should on my results. Otherwise I made a mistake, hopefully not. And then now obviously we can take the c that we have and plug it on our function here. It will look dirty, hopefully very simplifiable. Yeah. And when I problem again, they said largest interval. So since we have negative infinity to positive infinity, I don't even have to plug this thing back here to find the largest interval, because there's nothing bigger than this interval. It usually consists of any other interval that's possible. So let's try problem B. They said dt, I think they're talking about temperature, and that's time. Yeah, I think it's some cooling, I don't know, cooling theorem by Newton, cooling, something like that. Yeah, I see an ambient temperature here, and yeah, we're trying to model how the temperature behave over time. I think that Newton made this thing up. And then we're given initial value theorem at time 0. We have temperature naught, initial temperature, where K, and then they also told us that K, Tm, and T naught are constant, right? We have to make this thing look like we normally say. So our x here, or should I say, this function is changing in terms of t, right? Cool. So if that's the case, let me try to make it look proper. Let me make t prime here, and then kt minus tm. Oh, there is a k here. ktm. These both, it's a constant plus constant, so it's a constant, right? But this one is the one that has y, so I can take the other side, become t prime minus kt is equals to negative ktm. This is a constant, so this thing look like y prime is equals to plus g of x is equals to some p of x. I swap them, but this is the function that we want. This should be p of x here, then y is equals to some g of x. So our p of x in this case is this one. So we can say mu have to equal to e integral of negative k dt, almost said dx. Then from then you can find your, if I integrate here, I can find that this will be equal to negative k. T is my integration factor. What do I do? My integration factor, go multiply with it on our function. Let's just say that. And if I do, I get something that look like e negative k t. Let me call this t prime minus t e negative k t is equal to negative k tm e negative k t. Then this look like a product rule as we expected. Then whatever that is our first term stays here, and bring back whatever it was there, this, and here we only took this one, bring it here, and then the prime lost the prime because going back here is chain rule, product rule. Then I can now integrate both sides. Here I'll be left with whatever that was inside. Then my next problem will be integrating the right hand side. And if I do integrate this side, remember if I enter where I was, if I integrate here, this negative k, I'll have to divide by it, so I'll lose this one. So it will be just, I'll be left with tm and e negative k, but I'll gain a constant. So now from then, our t temperature in terms of time, I'll have to divide by this throughout. Then I'll be left with if I divide by this here, tm will be alone plus e k t. I think I also got a constant here. Yes, I have a constant here, and t is everywhere. T is element of, okay, fine. But now if you could look at this thing, it does look like a charging modeling equation. It also, yes, for temperature it makes sense because at time naught we should be getting our initial temperature that they told us. So yes, our results do make sense. Oh, they gave us initial value and they said T naught, temperature naught, and then if I put naught here, I'll have a C here. And then what was C? Temperature at time naught was T naught, they called it T naught. Then my C is going to be T naught minus Tm. And I have a C now. I can go plug it there and have a one equation that actually defines whatever that was going on there. So we just have to plug this there, then we are good to go. Remember, we use initial value to find what was our c? So our next problem, I think problem number 3, they're saying if in determining the integral factor that we've been using, no integration constant was introduced. Explain why if we evaluate that integration that we've been doing, but we are not taking in the c that comes with integrating there, or we are trying to find integrational factor. So the easy thing to say, if you look at the problem, mostly when they talk about constant, is that they will cancel. So the question is how they will cancel. So here you're expected to to explain analytically, not just saying they will cancel. But you've been noticing that every time we're using that, we're never taking out the constant. Okay, mu is a function of x. Let's start there. This one, you just saw it. Mu is a function of x. And if we have to... Okay, after doing, let me say you have y prime plus p of x, y is equal to some g of x. First we go out on the side, try to find mu, which is e integral p of x dx. I'm trying to answer the question why they don't add a c, or we don't add a c. So, and then we said if you get this mu, you kind of multiply by it throughout. So this mu gets in everywhere, the mu that you get here, right? And we said these look like it is a chain rule. Let's try to actually write what the chain rule will look like. So let me say I have mu and y. I'm trying to differentiate in terms of x. And the product rule, the product rule is supposed to be, I prefer writing mu prime, leave mu y as it is, plus leave mu as it is and y prime, right? So technically we're saying this blue part is the same as the other blue part, right? If what we're saying, these things are the same, then so for clarity, here they started with mu prime, so I should have started mu prime to make things easy with y prime. Doesn't change anything, I just told it to look exactly like that one. Leave that one as it is, plus do mu now, leave y as it is. So we're saying these blue things are the same. If this, okay, obviously the first term and the second, first term and the first term, they are obviously the same. But now what about the second term? The second term is mu px y. I'm saying that should be the same as mu prime y, because these things that we're saying are the same thing, right? And then if that's the case, I can just take out y, put there both sides, then I'll have mu px is equals to mu prime is literally d mu all over dx, right? And this is separatable now. We can take dx, put that side. I have p of x dx is equals to d mu all over mu. And then I can integrate both sides, and if I do, I'll have integral of p of x dx is equals to, this side I'll have ln mu, and then to make mu, so the formula I have to raise e both sides, and then mu have to equals to e p of x dx, of which this is not mu. That's what mu is, and it have been on our calculation. Okay, so how this answers our thing. But one thing I missed here is that the time I was integrating here, I got a constant. Let me call it c1, right? That means that c1 is going to be here, because it's going to be e power c1, and then that will be the same as, it will be another constant, so that's why I'm putting it just there. So that's what exactly our mu is. It's a sum constant and whatever that our mu was. So now we can go back to what we started with. I'll just rewrite it again because it's quite far to go there. So we started to say, if we differentiate some mu of x and y using a product rule, we get something that looks like that: mu dy dx plus mu px y. That's literally after you multiply by mu throughout. Alright. Okay. So if I can substitute this with a chain rule, so that it look like chain rule would have said mu y prime plus mu prime y. So that's where we started, right? But we got a mu that comes with c1 now. So here we'll have c1 e integral of px dx plus d dx of c1 e integral of p of x dx. That's what I'm integrating, right? And the y will go alone, and then here I'm supposed to have a y prime coming in with that. I'm actually copying that there, but substituting my mu, and then here my mu is going to be c1 espx dx. Then I'll have y prime, which is that. Then here I'll have plus mu goes with c1 e px dx, and the px and the y. But it's easy to notice here that you can factor out this, you can factor out that, it's also here, it's also here, it's also here. So this is the main reason why we can ignore the fact that we were having c1 prime. To finish it up, if I factor it out, let me call c1, you'll have d dx e. Let me know, there's no point, but you see, if we can write here and simplify it out, we literally tried to show us that whatever that happens, the c1 will be everywhere, and regardless of our choice for c1, you could choose 1 million, you could choose whatsoever, but whatever the value will be able to filter out from our solution. Okay, for I think this question 4, which is going to be the last part of the first half of our solutions, I'm going to do the exact equations. They have their own video because it looked like this tend to be a very long video. Yeah, so given these two sets of equations, systems, and then it wants us to, the question is, discuss how will you approach to solve this system and derive a solution for the system given initial value of x at t naught is equals to x naught and y at t naught is equals to y naught. So I think the most obvious thing that I would try to do here, dx dt is equal to negative 1 lambda, which is that one, I think to me this look really separatable. I can take dx and x here, and I'll have negative lambda 1 t. Then I can integrate both sides. I'm having ln x here, and then remember absolute. Then here I think I'm yielding out negative 1 t plus c, this constant that I get after integration. And then I can now raise everything by e so that I can have x alone here. And then this side I'll have e and negative lambda 1 t and another e to c. This is also a constant. It's better just call it k. So this is the k that we've been discussing in the previous question on why we don't add it on those integration type questions. Now, because we have an initial value, we can now try x naught. X at t naught is going to be x naught, right? That means x naught is going to, if I'm putting in x, I'll get x naught, then I'll have k here, e negative lambda 1 for t, I'll have t naught. So I can try to find k. K will be, I'll just divide whatever that is outside. I'll have x naught. This will be positive, which will literally go up. Okay, e lambda 1 t naught. So this is my k. So I can plug my k back to here. You can guess what will happen. I'll be having these things adding each other, and then the new x is going to be x of t, because the function will be x naught e negative lambda 1 t1 minus t naught. This is me if I add k here. I yield out this result. So for this side, it doesn't look like it will be separatable, so but I can use an integration factor. It's also linear. Then I'll have, let me call this one y prime, and then I'll take that onto the other side. I'll have pi lambda 2 y, and here will be 1 by 1 x. And let's look like what we normally have, and you can find our mu. It's going to be e integrating lambda 2 dx, and our mu is going to be e lambda 2 t. Then we can multiply by throughout there. Then if I do, then I notice the product rule thing, then I'll end up having d dt of mu lambda t. I'm skipping to some step to make a video quite short, and then this side I multiplied by whatever this is. I'll end up having mu e lambda 2 t, but we already figured what x was, so we can just go pick this x here, plug it here, and then if we do put x in where x is, end up having lambda 1 x naught e negative lambda t naught e lambda 2 minus lambda 1, all multiplying t. So from that we have to integrate both sides. Here we have x t y. The reason why I plugged in that x, this literally more of solving simultaneous equations. I have to take that value, plug it on the other side. Okay, so it's going to equals to okay, considering that you're integrating both sides here, I don't know how you're going to handle this integration, but you will get something that look like that. X naught e negative lambda t. The reason I'm skipping integration parts because it will make our video really bit longer, of which that's not what we are trying to teach, integration. Okay, then obviously we'll get some constant, let me call it d, right? And then from here we can solve you can solve your y, because that's what we want, and then your y of t is going to equals to, after solving for y in this very dirty long expression, it's going to look like lambda 1 all over lambda 2 minus lambda 1 x naught e negative lambda 1. I'm writing this for you when you're doing it. Try to see if you get the same result, but as far as I know, it's just a matter of you doing the math, nothing too serious, right? And then if I can simplify here, I'm getting x naught lambda e negative lambda 1 t minus t naught plus d e negative lambda 2t. Okay, the reason why I have lambda here, I'm actually assuming that I'm making this this expression just lambda. If you notice, this is not lambda 1, it's lambda 2. Literally assuming it's because it's a dirty thing to write, I'm making it very short. Okay, we also had another initial value for y, of which they said y at t naught should give us y naught. So if you use it here, you're trying to get rid of d, right? Because we got another constant. If you do that, you're going to get your d equals to lambda 2 t naught y naught minus x naught lambda. Remember, lambda is that. Then after that, we can get your y of t equals to x naught lambda. You remember what is lambda? E negative lambda 1 t minus t naught plus y naught minus x naught. Oh, there's a lambda here that I missed. Then e negative lambda t minus t naught. That is going to be our expression. We already have this is going to be our, we already have an x of t expression. Yeah, so we already solve x and y simultaneously. Please look out for the second part, of which we'll be doing exact equations from question 5 until, I don't know how many questions are there, but I think question 7. Thank you.